Let me briefly introduce Armand to you. He received his bachelor's in mathematics from Université Libre de Brussels in 1975, and master's degree from UCLA, and a PhD in applied math from University of Kentucky in 81. And since then, he has been a faculty of the Department of Electrical and Computer Engineering at University of Maryland, College Park, where he is currently a professor. He has held a joint appointment with the Institute for Systems Research since its establishment in 85. Professor Makowski's research interests lie in applying advanced methods from the theory of stochastic processes to the modeling, design, and performance evaluation of engineering systems, with particular emphasis on communication systems and networks. His more recent work has focused on random graph modeling for key pre-distribution in wireless sensor networks. Maybe when we can start, but let me just briefly check if we are connected to Facebook.
Maybe one of those is possible. So we don't have to wait then. So thank you so much for being here again. So start. All right. Thank you for the invitation. You can see it's a large audience. Today I'm going to tell you about a little piece of research that I've done over the last 18 months. Actually, more than 18 months. Most of it was done last year, when I was on sabbatical. And it's simple. It's fairly easy. You'll see you probably could have done it also one afternoon. All right. A number of pieces that I will kind of mention what they are, but I will not go into the details. But I think that although the topic may seem a little kooky at first, what you will see at the end is that there is a cautionary tale, and I will repeat the cautionary tale later in the conclusions, but the cautionary tale is that don't believe everything you read, okay? And don't even believe what I'm saying, okay? So without further ado, let me start, okay? The title hasn't changed. It's still as in the advertisement. And this is joint work with Siddharth Pal, who is now a postdoctoral fellow at the Army Research Lab near Washington, D.C. Okay, and let's start, as always, at the beginning. And what's the beginning here, right? We know, and you're probably familiar with that storyline as well, is that for the last 25 plus years, people have been interested in networks, or more generally in the science of networks. It started perhaps with telecommunication networks, but then, you know, in the late 90s, people started viewing the world out there not simply as individual components, but rather as an aggregation of components, and start thinking that, sure, each component has a local behavior, but what is really interesting, what's really important, is really to understand how the collectivity operates, what kind of behavior one can predict on the basis of the so-called local or individual behaviors of the components. Okay? And what we saw is that there's an emergence of something known as network science. Okay? It was pushed by the Army to a large extent. It represented an effort to somehow put science where at that moment there was really little science except a little paper here or a little paper there. Okay? And as always, when there is a new vanilla flavor of the month, what you see is surveys that are being written, because there's a lot of activities, especially under the funding system that we have here in the US. You start seeing a lot of papers, and so it's time to perhaps, as you see so many papers, to somehow aggregate the message of these papers, and that's basically what surveys are good for. Okay? And in many surveys, what do we see? We are being told one of the first topics that is being discussed has to do with the following. If you look at a network, you look at ways of characterizing networks. And one of the easiest way to characterize networks, one of the simplest way, one of the most natural way, is to look at the so-called degree distribution. Okay? Or to put it differently in a different language, is to look at a node and look at the size of the neighborhood of that particular node. In other words, to how many other nodes is that particular node attached. Okay? And what we hear in some of the surveys is something like this. We are interested in understanding how to model networks. We are going to focus on degree distributions. We are interested in a class of models that are known as random graph models, typically models that are generative, in other words, that there is a way by introducing some exogenous randomness that you will generate the links. And the first thing you read is that models out there are not like Erdős-Rényi graphs, which is really the simplest collection of random graphs out there. They're not like Erdős-Rényi graph in the sense that the degree distribution is not Poisson. Or to put it in contraposition, one starts with Erdős-Rényi graph, one looks at their degree distribution, and one is told that the degree distribution is Poisson-like. Okay? Now, what does that really mean? I mean, if you think about it, if you look at the survey, what you will see is an analysis that follows the following pattern. Okay? So GNP is a graph over n nodes. The little p here tells you that there is a parameter between 0 and 1, which is a probability. And you are assigning links between any pair of nodes with probability p. And you do this independently across all the possible pairs that you could construct. And there are n times n minus 1 over 2 such pairs. And it's really well known that if I denote by d and kp the degree random variable of node k in GNP, that random variable is actually a binomial random variable of parameter n minus 1 in p. Why? Because I take a node, I have n minus 1 that remain. When is it the case that I have a link between the one that I started and any other one that I choose? Well, it's a Bernoulli random variable with parameter p. These random variables are independent, they're ID. Therefore, the sum of n minus 1 Bernoulli random variables, which are identically distributed, is essentially a binomial distribution. All right, that's a well-known little fact. All right, and what is also noted, or perhaps you have intuited, but you probably haven't formalized, is that DNKP, because of what I have, let's see how this works, yeah. Because of this here, this really doesn't depend on K. So DNKP, these n random variables are actually identically distributed. They're not independent, but they're identically distributed. And just for simplicity, for later on, I will denote a generic 1, I'll denote it by DNP. And so if you think about it, when I have a Erdős-Rényi graph, I can tell you something about a degree distribution because every node has the same degree distribution. Okay? And the theoretical justification behind what I had put over here is what's at the bottom of the line, of the bottom of the slide, which says that there is something known as Poisson convergence that says that if I select p as a function of n, if I scale p as a function of n, and I do so in a very particular way, I do so that p sub n is roughly like lambda over n for some lambda positive, then as n goes to infinity, this generic degree random variable converges in distribution to a Poisson random variable. It's a very, very simple result. You can do it by hand. There are many, many different ways you can do this, but this is very, very well known. Okay? So you're being told degree distributions are important. We are looking for random graph models. You look at Erdős-Rényi. Erdős-Rényi is Poisson-like. Okay, so very happy. But the next page, you're being told that, in fact, the survey is really not about Erdős-Rényi graphs. Why? Because if I look at the data that is collected out there, what you realize, or what people realize increasingly, is that if I look at the degree distribution of the various networks out there, in fact, there was no Poisson-like signature. It was something else. In fact, what you often hear in this survey is the following fairly vague statement that says that for large networks, and most networks in practice actually large, right? So if n is the number of known, we are considering the situation when n is large. And then the statement reads like this. N sub n of d over n is the fraction of nodes that have degree n in this network over which you're collecting the data. I'm sorry?
Fraction of nodes with degree
That's right, with degree d, yes. Okay. So if n sub n d is the number of nodes with degree d in G of n, then n sub n d over n, what people have observed is that it often has the form c times d to the minus alpha. And how do they figure this out? Well, they typically take the log of this ratio, and what do they see is that the log as a function of the log of d becomes, in fact, a linear function. Now, it's very approximate, all right? But network after network after network, you see this signature that emerges. Now, why am I saying that it's a vague statement? Because n is large. Nothing is really said as to how large d is in relation to n. And I'm really not telling you really what this little equal giggly really means, okay? All what I'm saying is that if you look at many, many, many papers of 20 or 30 years ago, what you will see is a log-log plot that for a large period over the area where you're concerned, it's actually linear. And sure, once in a while it drops at the end, but that's because there's not enough data, really. Okay, so this is where you start seeing in these surveys, you start seeing the notion of a power or Pareto-like degree distribution. And that's where you start hearing about this notion of a scale-free network. Why scale-free? Because if I look at a Poisson random variable, there's a natural scale. And the scale is given by the lambda, which gives me the average. Okay? And everything is then recentered about the lambda. In this, there's no natural scale. There's no lambda floating about. The only parameter that you have is the alpha here. And in fact, I should add that in most data collected at that time, the alpha roughly was between 2 and 3. Okay? In fact, closer to 2 than to 3. So you say, okay, that's interesting. It means that I shouldn't rush to the library and learn anything I want to know about Erdős-Rényi graphs, because the action is not really about Erdős-Rényi graphs, it's about something else. Okay? Now, one natural question is, well, if Erdős-Rényi graphs do not provide this kind of degree signature, then are there other models that will generate this? And this is where a very influential paper by Barabasi and Albert comes about in 1999. And I think that in January of 2015, I looked at the citation count. It had over 21,000 citations. So imagine what it is now, almost 18 months later. Okay? It's a highly cited paper. It provides or produces a model. It's known as a preferential attachment model. It's a generative method, and I'll come back to it, where you have a collection of graphs that is generated in a somewhat Markovian type manner. So G of n is the nth graph. It has node set Vn, and this funny En is essentially the random set of edges that is generated according to the recipe that I will describe in a moment. Actually, not in a moment, but in a little bit later. Okay? Unfortunately, now what we see is that because it grows, and because of the nature of the preferential attachment algorithm that you're using, it's no more the case that the degree, if you look at, for example, a G of n, which is a graph over a node, it is no more the case that node 1 and node n have the same degree distribution. In fact, as n increases, the degree distribution really are changing as we step through n. Okay? Now, what is true, though, is that if I look at the same quantity that I introduced earlier, so n sub n d is the number of nodes in G of n that have degree d. If I denote by p sub n of d the fraction of such nodes, what do we see? We see that the limit of P and D as n goes to infinity converges almost surely to some number, which I would call PSFD. And PSFD is in fact a probability mass function on the non-negative integers that has this particular property. In other words, that as D gets to be large, this behaves like C, some constant, times t to the minus 3. So what you see is that this is indeed a model that provides you with a scale-free distribution for the degree. Right? Now, a lot of people have worked on this. As I've said, in 1999, Barabasi and Albert introduced this in the, I think it's in a Nature's paper or Science, I don't remember exactly where. In 2000, Bolobash and Riordan actually gave a formal proof of this result, because in the original paper it was really a hand-waving argument. And many, many people have looked at this problem in the following sense, that there have been many different variations of this model. And again, the holy grail is always to show that this fraction of nodes that have a particular degree, basically, as n gets to be large, goes to a limit, and that limit has this power law, has this tail. Okay, that's basically what if you contract the literature into a dot, that's basically what you could say. Okay, now,
So
yeah.
here D is not Dm, right?
No.
You don't scale.
No. Okay.
So yeah, again, D is not scaled with n. So you let n go to infinity, P and D converges to some function of D.
That's right.
And then you are saying this function as D gets larger and larger,
That's right.
looks more and more like D to the minus 3 times
That's
the
right.
constant. Okay.
Okay. Now, if you step back and you remember what I said in one of the earlier slides, and you look at this, somewhere there has to be a cognitive disconnect, right? Why? Because what did we do in the context of Erdős-René? We had dn1p, dn2p, and so forth, dnnp, okay, for a given n. We noticed that these n random variables had the same distribution. I called it d sub n of p. And what I told you is that when I take p and I scale it with n as p sub n is equal to lambda over n, that dn p sub n converges to a Poisson random variable. Yet, if I look at the result that I put on the previous slide, that's not the kind of result that I am talking about. What I should have told you about the Erdős-René graph is whether or not, this doesn't seem, yeah, that this, okay, which is essentially the fraction of nodes in Gn Pn that has degree D, I should have shown that this actually converges to the Poisson limit. But I didn't. So in other words, from the word go, what we have, it seems, is a discontinuity or a disconnect, a cognitive disconnect, because Barabasi-Albert talks about, if you wish, an experimental or an empirical distribution, while the Poisson convergence result is about a degree of a particular node, which is the same for all nodes. So the question one can ask, is there a relationship as n gets to be large between this, forget about the k here, as n gets to be large, and this as n gets to be large? This has a well-defined distribution for every n and every p sub n. This is also a random variable whose distribution is much harder to characterize. The question is it the case that when n goes to infinity, these two quantities coincide? I'm going to say, I don't know. Okay? So you think about the problem, and what you prove is this little lemma that says that everything is fine. In other words, that maybe whoever wrote the survey wasn't aware of the discrepancy, but there's no harm done because at the end of the day, it's okay. That D and P sub n converges to Poisson, and the empirical distribution also converges to Poisson. So the fact that maybe he or she was confused when writing the paper is really of very, very little consequence, right? So basically, when we compare Barabasi-Albert with Erdős-René, we cannot compare indeed the pairs with the pairs, the apples with the apples. Before we could. Now, I'm not going to tell you now how I prove this, so not too difficult a result, but I'd like to expand the issue, and I would like to look at perhaps a general framework where I'd like to prove results like that. Okay? So what's the setting? I put myself in a setting where I have a collection of random graphs, okay, where G of n is a random graph on n nodes. Okay? Let's dn1, dn2, dnn be the degree distribution or the degree random variable for node 1, node 2 up to node n. And let's assume, as we had with Erdős-René when we did the rescaling, that dn1, dn2, and dnn, these n random variables have the same distribution. Let's call the generic, let's call it d sub n. Okay? Now, question. If d sub n converges in distribution to d, is it always the case then when I look at the empirical, which is this, that this will converge in probability to the same limit as where d of n converge? Remember that in the Erdős-René case, here we use the scaling lambda over n, d was Poisson, and what the previous result showed is that indeed we had coincidence of the limits. Okay?
So what you have over there is probability of capital D being equal to it's the expected value of what you are having on the left-hand side, right? The fraction.
Yes, that's right.
It is
that's
the
right.
expected
That's
value.
right.
So
but
you are asking the question whether this thing is converging in probability.
That's right. That's right. That's one way to look at it. Okay? But there's no guarantee that because the expected value converge. That's right. That's exactly right. Okay? So the answer is exactly as Osman says, yes, provided that certain conditions are satisfied. And there are three conditions that need to be satisfied for this to happen. The first assumption is an assumption of homogeneity. We've seen already one piece of it because we needed it in order to formulate the problem. But we're going to ask actually a little bit more. We're going to ask that anytime I take a pair of nodes, K and L, that the degrees of these two nodes have the same distribution as the degrees of 1 and 2. Okay? Clearly, if this is true for every K and L distinct, this automatically has to be true. Okay? So this is subsumed by this. So you have an assumption of homogeneity. The second assumption is the existence of an asymptotic degree distribution, as we had in the formulation of the question, under assumption 1, because now, remember, this does not depend on K anymore, under the assumption 1. Is it the case that dn1, the d sub n that I had before, does it converge to some random variable d? And throughout the talk, let's call P the PMF of the limiting random variable d. Right? So these two conditions are natural in order to simply talk about the issue. Simply in order to formulate the question, you need assumption 1 and assumption 2. Assumption 3 is really the one that really makes everything work, and it's a form of asymptotic uncorrelatedness in the following sense. Assume that we are under assumption 1, okay? And look at the two binary random variables, characteristic function that dn1 is equal to d, and characteristic function that dn2 is equal to d. Assumption 3 is going to require that these two random variables are absolutely uncorrelated in the sense that if I look at their covariance, as n goes to infinity, this goes to 0. Right? Now notice that I can rewrite this in this particular form, right? Because this is the e of xy minus e of x times e of y, and I want that covariance to go to 0. Very weak assumption. Usually, you are likely to establish 3 by asking something stronger. As you can imagine, what you would probably like to do is to ask, and that's assumption 4, that under assumption 1 and 2, under assumption 1 and 2, you're going to ask for the degrees, random variables dn1 and dn2, to be asymptotically independent in the sense that dn1 and dn2 as a pair converge jointly to a random variable, to a pair d1, d2, and d1 and d2 would have the same distribution as the random variable D that I had in assumption 2, and D1 and D2 are going to be independent. And if you go back to this, right, if you go back to what assumption 3 really tells you, what you see is that because of the convergence of D1 and DN2, DN1 and DN2 in distribution, this will converge to the probability that D1 is equal to D to D, D2 is equal to D, and this will converge to the probability that D is equal to D, and D is equal to D, and therefore, to us that it be 0 means essentially that D1 and D2, the characteristic functions, are uncorrelated, and clearly that's implied if D1 and D2 are independent. Okay, so that's really even asking more than you need. Okay, so let's recap the assumptions. We have two that are basic, the first two that are basic to the formulation of the problem. We have the third that tells you something about some form of uncorrelatedness. We have four that basically is a stronger assumption that allows you to check 3 without having to sweat, provided that, of course, that you can get 4. Okay? Now, assumption 4 implies assumption 3, we've seen. But notice that assumption 3, as I had it here, right? If you look at what I have here, this does not require the convergence of the pair dn1, dn2. It does not. All it does require is that this difference go to 0. Having said that, we are at the main result, and as Osman said, this is essentially some form of the law of the weak law of large numbers. And let's see why this is so. Okay? The theorem says that if I look at my setting under assumption 1 and 3, then this ratio indeed will converge to P of D in probability as n goes to infinity, where I remind you P of D is the probability that cap D is equal to little d, where cap D is the limit for the weak limit that is assumed to exist for dn1 as n goes to infinity. Okay? Now, it mimics the proof of the weak law of large numbers. And so what is the proof? The proof is essentially to look at Chebyshev's inequality. Right? So you want to show that this is going to go to 0 for every epsilon, because that's what this is really saying. You know that you can bound this by 1 over epsilon squared, the second moment of this absolute value, and that's essentially what you're getting. Okay, now let's see why, indeed, everything is in place to obtain what we need. As we will see in a moment, to prove the result in proposition 1 is essentially equivalent to proving something much weaker than that, or seemingly much weaker. This is what assumption 2 tells you. It says that if assumption 1 and 2 hold, then this variance that you wish to drive to 0, this limit has a limit which is in fact exactly the limit of the covariance that enters assumption 3. So you can see where this is going. I want to prove that this goes to 0. So to prove that this goes to 0 is essentially equal or equivalent to proving that this goes to 0. Right? So another way to say this, the result is really, under the assumptions that are being made, is really about considering this covariance, and if you are able to show that it converges to 0, you're done. Now let's see why this is so. Remember that we want to show that this goes to 0. So what are you going to do? You're going to put in the expected value of the random variable, and by standard properties of the variance, it has to be, this expected value has to be equal to this. Has to be equal to the variance of the ratio plus the square difference that is here. I put the n outside, so I have a n minus 2 variance of n and d, and then I get this term. Okay? Now, as I think Osman already intuited, this is likely to go to 0, certainly under the assumptions that we have. If you didn't see it, here's the reason why this is so. It's because if I look at this expected value, by linearity of expectation, this is what I'm getting. right? And under assumption 1, this does not depend on k, therefore it's n times the probability that the n1 is equal to d. Right? So that if I divide this expected value by n, so is this? Yeah. If I divide this expected value by n, basically I'm getting essentially this probability, and as n goes to infinity, this by assumption 2 goes to PD. Okay? So clearly, the second term that we had on the previous slide goes to 0. So the only thing that needs to be considered really is the first term. So let's look at the first term. Let's look at the variance. And let me remind you that the variance is the sum of indicator random variables. So you're going to get n terms which correspond to the diagonal. But remember, a characteristic function, when you square it, it's itself, because 0 square or 1 square gives you 0 or 1 respectively. And you are then getting n times n minus 1 terms, which are the diagonal terms. If you put all of this together, this is essentially what you're getting. Okay? Now, because of assumption 1, the n terms that are on the diagonal collapse into n times the variance, while the terms that are off the diagonal collapse into these n times n minus 1 terms here. Because the fact that you have k and l, basically by assumption 1, is the same as taking 1 and 2. Right? So I divide this variance by n squared. What do I get? I get the variance here is divided by n squared, by n, so that's the first term. And then what's left is n minus 1 over n. Right? Now n goes to infinity. What happens to this variance? Well, this is bounded by 1. Therefore, if I divide by n, it goes to 0. So in a sense, the variance, the original variance going to 0 is the same as having this term going to 0 under the assumptions of the theorem. And basically, this would amount to what? To the covariance here going to 0. And that's exactly true, because that's assumption 3. Okay? So what we see is that we have, under assumption 1 to 3, we have the result, but most perhaps important for what follows is lemma 2, if you thread back the proof, that says that this convergence, the convergence of the expected value here, is equivalent to the convergence of this covariance. And the way to read this is that this having a limit, this limit occurs if and only if this limit occurs and they are equal, under the assumption 1 up to 3. Yes, you wanted to?
So in this bottom equation, don't you need a middle, like cross term as well? So you subtract and add the expected value of n and d over n. So I get the first term, which is the expected value of n and d over n minus expected value of that squared. The second term is fine. There needs to be some 2 times the multiplication of these two guys, right?
No, because you're gonna subtract the deterministic term, so that when you're gonna do the cross, you're gonna get this minus its mean, and it's gonna give you 0.
Oh, yeah.
All right. Right. I mean, it's the basic argument as to why the mean happens to be the. Right. That's right. Okay. So, are we clear on what I've done here? So basically, what I'm telling you is that this is really an easy result. If you had understood the weak law of large number in its proof, you could have done this in the afternoon. Okay? And basically, the assumption 1, 2, and 3, 1 and 2 come about from the problem formulation, and 3 is essentially saying, what is it exactly that I need for that variance to go to 0, or this expected value to go to 0? Okay? Now, observe that you could argue that this result is a result about convergence in L2, because I had the Chebyshev inequality. I showed not that the probability directly went to 0, but I showed that the expected value square went to 0. So that's an L2 convergence. Okay? However, and that was Chebyshev's inequality's responsibility, if you wish. But if you think about it, so what does that mean? It means that L2 convergence imply convergence in probability, but it's also well known that for bounded random variables, convergence in probability implies convergence in L2. So the result that I got you is really the best I can do. There is no wiggle room between L2 and convergence in probability. That's one thing to note. Okay? Now, So what does that really mean if you contrapose my observation, my last observation? It means that if I look at the convergence of this sequence, right, it will fail in either mode as soon as this limit exists and happens to be positive. Because if this is positive, then this will be positive, and therefore I will not have L2 conversion, and therefore I will not have convergence in probability. Okay. All right. So you say, okay, Makowski, that's nice. It was easy. I could have done too. I mean, no questions about it. Okay, but are there really many situations where this occurs? Right? I mean, you could argue, you know, it's as they often say in logic, right? All the elephants are pink on the empty set. Okay, I mean, you know, it's not false, but it doesn't exist, so who cares, right? So here is maybe a couple of slides to tell you that, in fact, this situation occurs in many settings. In fact, for most graphs, graph models that I know, this little theorem basically applies. Okay? All right. So what's the setting that you encounter in many applications? It's something like this. You have an underlying parametric family of random graphs. So let's call that family Gn alpha. So remember, n is the number of nodes. Alpha is some parameter that lives in some subset of Rp, right? For example, think of Bernoulli, right? Not Bernoulli, think of Erdős-René. For Erdős-René, the alpha is the little p that we had before, and the little a here is essentially the interval 0, 1. Now, typically, in many settings, for many generative random graph model, for each alpha, the degree random variable, dn1 alpha up to dnn alpha, are exchangeable. Right? That's one thing that you notice in many settings. And in also many settings, there exists often a scaling, let's call it alpha star. So what is the scaling? It's a sequence of parameter values that depend on the size of the network, such that dn1 alpha and star converges to some random variable. So for example, in the Erdős-René case, what is alpha n star? It's lambda over n. Right? And what is d? Well, d is that Poisson random variable that I started with. Now, this is often the case because in many situations you have what's known as a maximal component, and the alpha star is often related to the existence of this maximal component. Take an n, take Gn of alpha, and replace alpha by alpha n star, and let's call that graph G of n, thinking of G of n as one of the graph in the sequence for which I developed the theory a moment ago. Notice that assumption 1 and assumption 2 are automatically satisfied under the exchangeability conditions that I've put forth, as well as because alpha n star has the properties that it has. So the condition that need to be satisfied or to be verified is essentially assumption 3. And if you're lucky, maybe you can look actually at assumption 4, because if you have assumption 4, you have assumption 3 that is true. Okay? It turns out that there are really a very long list of models to which you can apply this. Okay, we have looked already at Erdős-René graphs. You can look at so-called geometric random graphs. You can look at, for some of you here who are familiar with what has been one of Osman's obsession during his PhD thesis, is random key graphs, and the list goes on and on and on and on. Okay, so again, at this point, you say Makowski is getting to be a little simplistic. Okay, you had a question, you had a little framework, you had an easy theorem, and what you seem to be saying is that, you know, almost everything that you will encounter out there is gonna be good. In other words, it's gonna have proposition. I mean, proposition 1 will apply and give me the equality between these two limits. Okay, all right. You say, okay, fine. So is it always the case that I have assumption 1 and assumption 2? It automatically implies assumption 3. And so what I'd like to show you is a little counterexample. And the counterexample is interesting not because it says that maybe you should once in a while perk up, all right, especially in the middle of the talk, but because this particular counterexample is one of these counterexamples that is floated in the literature, and as I've said before, do not always believe what you read. Okay, exercise critical judgment, because it turns out that the storyline associated with that model is in fact incorrect on the basis of what I'm going to tell you. Okay? So in case you're losing me or I'm losing you, usually it's a symmetric relationship, okay? Let's make sure that you've got the message. So what's the motivation? Let's go back to the preferential attachment model, right? Remember, this is a model that was introduced to be able to say, hey, there are random graph models that exhibit power law degree distribution in the sense understood by Varabasi, in other words, as the empirical converges to a distribution that has some appropriate behavior at infinity. Okay? Now, what is the preferential attachment model? As I've said, it's a model that is what's known as a growth model. So you start with one node, you had a second node, you have two nodes, you have third node, and so on and so forth. So suppose that you've already created the model with n nodes, and the n plus first node comes along. So you already have a graph over n nodes, the n first ones. The arriving node looks at the degree of each one of the existing nodes and attaches itself to one of the nodes with a probability that is proportional to the degree. Right? And this is why this is known as a preferential attachment model, or also sometimes as the rich get richer, right? Because being rich here means what? Means that you are attached to more, and so if the probability is proportional to the degree, it's clear that the more nodes you already have in your neighborhood, the more likely it is that someone will attach itself to you. Okay? Now, this model, as I've said, created a little cottage industry. There are many variations to this, all right? I mean, it's, some of it is interesting, some of it is, well, someone has to write a thesis, so, all right, the paper gets written, okay? But if you look at it from a modeling standpoint, the moment the ink, even before the ink was dry, people argued that, sure, it's true that this model will generate a power law distribution. Unfortunately, it does so through an algorithm which may not be applicable in some situations. Because what does this algorithm say? It says that as the new node comes in, he or she, because we're in 2016, has an opportunity to look at the degrees of each node. Well, is it really realistic that in many situations that information would be available? There are situations where your number of neighbors, the number of people with whom you have a relationship, is not something that you advertise on your forehead. Okay, therefore,
I was going to ask one thing, but you can't.
Yeah. So, is this really? Sure, there are probably situations where this is true, but there are probably a lot of other situations where you find scale free, but you don't have, for the incoming nodes, the ability to see all the nodes and their degrees. Yes?
So do you have to look at it like, okay, new guy is going to come and then he's going to pick, he or she, he's going to pick one from the n nodes and it's going to be... So another way to look at it is as follows, right? So you have n people, everyone has a degree, and we are this n people, and one of us will bring a new guy to the club, right? And the more connected we are maybe more likely to be the one who brings the next person. So this doesn't really require for the new coming person to know actually the degrees of everyone, right? This is just a...
But how would they attach themselves?
So I'm not saying it's like... So we are n people, everyone has a degree. One of us will bring the n plus first person, and because of the mechanics of how social relationships, are created, the one that already has many friends is the one that is more likely to be the one that brings the n plus first person. So it is more natural.
Suppose that you and I were already in the network, okay?
Yeah.
And you, because you're a chatty kind of guy, you already have 200 friends. And I, because I'm so taciturn, I have maybe 2 friends. Okay. How are we going to generate? How do you know that I have fewer than you, for example?
Well, I don't have to know it. It's just whatever we do to bring new people in, somehow there is maybe some underlying social mechanism that creates this proportionality.
But I think that the nature of the criticism was based, I think, on the fact that the preferential attachment mechanism is one that somehow mimics what is actually happening in practice. Because remember, this is a generative model, right? It basically says nodes are coming in, they need to attach themselves to one of the nodes that are already existing in the network. What information will they use in order to do that? Okay.
I mean, it's just like semantics at this point.
I don't think
it's more like, what if you? I mean, it's a model, right? Yeah, it is like, yeah.
But still, at one point, someone has to know the degree distribution.
So it's just a model where you say, the more friends you have, you are more likely to be the one to pull the next guy. That's one way to look at it. Your way of presenting is there is already a guy just appeared from under the ground, and then he has to now decide whom to join, and that's so based on the degrees.
Yeah, but I don't think that you avoid the issue of comparing the degrees, because you're saying it's not pull or push, okay? I mean, but at the end, suppose we're already in the network. Somebody else comes in, okay? You are, I think in your head, you have a view of a strength, right? Of a strength that is attached to you, and you're comparing somehow my strength versus yours. So someone has to know the strengths somewhere. Well, at least what you can do is this, okay? Okay, maybe this is what I think you mean, right? Is that we can do this pairwise, maybe. That's what I think you may be suggesting. But, right, because the fact that we're normalizing is not really that important. Right, so for example, if you share with me your degree, right, then we can probably have an experiment and decide who will have. Okay, then I go to a third person and we do the same thing, and that is probably equivalent. But that's just a question of implementation.
Like we both apply to a grant. One way to look at it is like you get it because you are better. The other way to look at it is given to you because you are better, right? I mean, it's a bit like, so you are saying like the person who is going to decide is to know your strength and my strength, and then has to decide based on that. Another way to look at it is this natural process. You and I compete. We don't have to know each other's strength, but somehow the outcome is like Mother Nature knows it.
But how would you suppose I take your viewpoint? Okay, how would I implement this on a computer, for example?
Well, the computer is to know.
I don't know. But you could argue that maybe I have a distributed implementation, which is what I'm suggesting a moment ago. Okay, and then I'm certainly willing to agree with you that there doesn't need to be perhaps a single entity knowing all the degrees of the
and
nodes.
It could be like there is a ballot box. Each of us are putting as many balls that has our number as the degree of us, and then God picks one random.
But so that's a distributed implementation, right? I mean, I think but usually that's not the way it's presented, right? The way it's presented is, and I think the criticism was, I think, given in the context of that it was presented, that if you believe that this is a generative model and basically the new person has to know, or at least someone has to know the information. And by the way, even in the box, right? And again, there you will argue that everybody puts their degree in there without knowing. Okay, but still the mechanism has to somehow know all the values. Okay. No, I'm willing to see that maybe you can do this in a distributed manner, right?
Yeah.
But
I mean, I agree with the
Okay.
criticisms
Okay.
about the model. I mean, it's
Okay.
just, yeah.
All right. So the point is that the ink was not even dry, and people already start complaining that this is not a good model, at least in some situations. Okay. So around probably 2002, a group of physicists, Caldarelli being the, I think the kind of the most prominent one, who proposed another class of models, and these are known as hidden variable models. Okay? And the idea here is quite different. And again, I will come back to the same criticism that I think you're raising, but in a different form, is that the reason why people attach to each other, the reason why people have connections, is because they have an intrinsic utility or an intrinsic value, and it's on the basis of that value or utility that the connection gets is made, and it's done in a probabilistic manner. I'll give you an example. Suppose that we live in a world where money is all that matters, really. Okay? And one can make an argument that the only way people really relate to each other is that they want to know if you have enough money for them to play with you, right? So if you have a certain value, a certain monetary value, and I have a certain monetary value, we're going to have an association only if, perhaps, maybe the sum of our worth is greater than some value, for example. Okay? These models, known as hidden variable models, have many forms. Okay? Some are very complicated. They've been studied by physicists, but there is one in particular that I will describe, on which one can really do quite a bit of analysis and that can give you some interesting insight. Okay? So these are the graphs which I know, or that I would call as random threshold graphs. Okay? Node I has a fitness value, let's call it Xi. Okay? And let's assume that these are ID random variable, and let's denote by Xi the generic. Okay? And before we had that the rich get richer. Here we're going to have something a little different. We're going to have that the rich know the richer. And it works as follows. Okay? We have a threshold theta, which is a scalar. And we will say that the node I is connected to node j if and only if the wealth of I plus the wealth of j is no less than theta. Okay? And we're going to call this graph a random threshold graph, and we're going to denote it by T for threshold and theta, and for the number of nodes, and theta for the threshold value that we are using in its formation. In fact, we're going to specialize to the case where the Xi random variables are non-negative. Okay, these fitness random variables are assumed to be non-negative, and in particular, we're going to consider one important case. That's the case when the Xi's are I, the exponential random variables. And because the X's are non-negative, it's enough, of course, to take theta to be positive. As I've said, there's a huge body of literature already on such graphs, okay, especially in the physics literature. And in particular, there's one interesting result which attracted the attention of people like Caldarelli and which allowed them to make the statement that they had a better model. Okay? And what is that statement? Is that in this model as well, you can find power laws. Okay. How? Well, if I look at the case where Xi is exponential, right, where in other words the fitness is an exponential random variable, let's say with parameter lambda. Well, if I replace theta by theta n star given by 1 over lambda log n, well, it turns out that the degree distribution is in fact converging to a random variable which has a power law. Okay? And so basically what that would say is that here is a model that doesn't use preferential attachment for which I have scale free. Right? Now, if you think about the criticism that was given for the preferential attachment, you can say it's a little bit bogus also, but it's a little less bogus perhaps, because there one can make the argument that it's not that a genius has to know the Xi1 up to Xn. In fact, it's any pair of nodes. Basically, they show it, perhaps in secret, they show their fitness and they decide on the basis of that. Now, one could argue back and forth as whether or not this is a better model or not, the only thing that is put forward is that this theorem suggests that the degree distribution can also be parallel. Now, remember, these are models, they're proxies, they're little toy examples where you can show that certain nice probabilistic properties actually occur. Okay? I personally never view these models, the Barabasi model or this one, as models of reality. They're only proofs of concepts that you can make certain properties arise by doing very, very simple things. In other words, that the local behavior gives rise to certain properties in the large as n gets to be large. That's the only way I interpret this. Others are much more orthodox and view this really as real models. I would not. Okay? But that's beside the point. Okay? So having said that, let me kind of reinforce what I've said before. There is a result, which was on the previous slide, which was proved, I think, formally by Fujihara in 2003, that says that if I look at dn1 theta n star, it will converge to D, and the distribution of D, the PMF of D, is this P Fujihara D, which is given by this. And notice that this is a Poisson PMF, but it's a conditional one in the sense that the lambda that we had before is now e to the lambda c, which is a random variable. Okay, and this is why you have the e to the minus e to the lambda c. And on the basis of this result and results like this, that we have Caldarelli claiming that the random threshold graph with exponential fitness provides an alternative to the preferential attachment model due to the fact that this limit here behaves in this particular way. In other words, it's not exactly what you find in Barabasi-Albert, because Barabasi-Albert had 3, but here you have 2. And this, of course, gives rise to the possibility that in this class of models you can find probably something, all right, that has a 3, maybe a 3.5, whatever you want. Okay? So that was the claim by Caldarelli and all the people who did this kind of work, thinking that hidden variable models are honest-to-God competitors to Barabasi-Albert. Okay? Now, is this true? Is this false? What? Okay? Now, here, in order to apply the results that we had, you need to do what? You need to look at G of n, which is T sub n, where theta is replaced by theta n star. Okay? Assumption 1 clearly holds by symmetry, because this is a fully symmetric or changeable graph. Assumption 2 holds by what I had put over here, because it's indeed the case that dn1 converges to a distribution, converges to a random variable D, and its distribution is this P Fujihara that I mentioned a moment ago. And so then the question is, of course, is assumption 3 holding here? And it turns out that assumption 3 fails miserably here. In fact, if you look at this here, which is what you need to choose, whose limit you have to evaluate, it's easy to see that, easy. You can show that C of D is in fact positive for every D. It's not 0. If this is not 0, by lemma 1, the expected value of the square doesn't go to 0, and therefore I cannot, the theorem, the basic theorem does not hold, since assumption 3 cannot hold in this particular case. Okay? And in fact, to give you an example, if I take D is equal to 0, what you find is that C0 is in fact given by this expression, and it's not difficult to see that this is in fact strictly positive. Okay? Now, I'm not going to give you the proof, okay, but I'm only going to give you kind of a sense of the, actually not even that, okay? Let's go further. Okay, so now we don't have that the empirical distribution converges. So we have that dn1 theta n star converges to Fujihara. We don't have the frequency distribution, or if the empirical distribution doesn't converge, right? So therefore, the claim of Fujihara is simply incorrect. In other words, that the model of a random threshold graph with an exponential fitness simply cannot be a substitute for a Barabasi-Albert model. Okay? Despite the many, many papers that are written that seem to vehiculate this particular idea. Now, it's okay. You've shown essentially that this does not converge in probability to P Fujihara D. That's essentially what I've shown. Okay? So the question that you can ask is, does it converge at all? Right? It doesn't converge in probability, therefore it's not going to converge almost surely. So what's the next thing? Does it converge in distribution? And it turns out, and that's actually not that trivial to show, is that if you look at this fraction of nodes that have degree D, this indeed converges to a random variable. Let's call it pi of D. And this pi of D is non-degenerate. Again, I'm not going to give you an idea of the proof. I will stop here, but I will say the following. If you go and you look at the papers where Caldarelli and his cohort are claiming essentially what I've mentioned to you a moment ago, there's plenty of simulation work. Okay? And the simulation work seems to suggest convergence. And why is that? Because typically what happens is that if you're going to prove that this is going to converge, right, by simulation, what are you going to do? You're going to run multiple replica, IID replica of this situation, and you're likely to take the average. But if I do that, what am I going to get? Well, what I'm going to get is, in fact, the expected value of this distribution, and that turns out to be exactly P Fujihara of D. And so simulation is great, but you have to be careful, because if what you are trying to show doesn't exist or is not true, well, you will run into trouble, because you are not going to show either that it converges or doesn't converge, because all what you would have shown really is that the average converge. But that's not what we were setting out to do. Okay? All right, so if I have to conclude, because you've been quite patient, okay, is that when you look at networks, I think perhaps one should be a little bit more sensitive to the notion that there is something like the degree of a node, and then there is a kind of a network-wide notion, which is this empirical distribution. Okay? When n is large, under the appropriate scaling for many, many, many settings, it's the same thing. But there is one important example, for reasons that I explained, where that is simply not true. In fact, it's embarrassingly not so. Okay? And as I've said before, preferential attachment and hidden variable models do not play on the same field. For the first one, you do not have the degree of a node generically. You have only the empirical distribution, while for hidden variable model, it's just the opposite. You have the degree distribution of a generic node, but you do not have that the empirical distribution converges to the appropriate limit. And as I've said again before, when you read something, if you don't understand, don't be afraid, because probably it may not actually always be true. Okay? All right, and I'll leave it at that. Any questions? There's still, yeah.
Yeah, let me keep going. I mean, as you know, right, the work I have done, we have done together, it's always the degree. There is no such question of Poisson or anything, right? It's always going to infinity, because that's what is needed to get connected. So did any of these people touch that? I mean, it's always like probability of an edge seems to be a constant divided by n, so that on average it's a constant. But what happens if lambda is also a scaling, and then it's like log n over n? I mean, of course, there is no hope to get a Poisson distribution or anything, but is there any way to still say this is practical, this is more like a social network, or this is not, or why so? I mean, what
no, I actually, you know, I think there's a lot of work trying to model social networks, right? I mean, you hear everybody has a model, I mean, because of what I like to do, I kind of like generative models, but I think I've come to the conclusion, perhaps, that generative models for social networks may not really be appropriate. Certainly not random graph models. They're certainly appropriate in engineering situation where there is a kind of a natural randomness, right? For example, if you want a model of a wireless sensor network, you have an area, you plug your points at random in an ID manner, you could reasonably argue that the position of the mobiles is by and large random. Okay, and one can make an argument that that's so. Okay, maybe they're not ID, but it's certainly random. Okay, because you don't really know where people are going. Okay, in the case of the random key graphs that we've studied, I think that the case is even better there because the graph is generated by the cryptographic constraints that you're imposing, and those are part of the algorithm, right? With a social network, when you look at Facebook, well, Facebook is one instantiation, right? It's, I think, very, very, very difficult to argue that it's random. I mean, there is, of course, always some randomness, but how to capture that randomness is, I think, quite tricky. And I'm not even sure that if you had a good model, you would necessarily be able to validate it in a way that is coherent. So I think it's fun. I think there are lots of very, very interesting models of social networks, or allegedly of social networks, that you can generate. I view them more as choice situations where you are creating ensembles of graphs that have certain nice properties, so that, all right, perhaps the mechanism that create these graphs maybe have something, it puts some meat on the bone, so that you can think perhaps, like with Berabasi, right? How do people form network? Well, we always go towards the more popular guys, right, or girls, right? I mean, that's right. I mean, certainly it makes for good copy, it makes for good conversation. Whether or not it's really true, okay, perhaps. Okay, I read them. Okay, just. But I would, if I were to do random graph modeling, I would do it more for engineering applications than for social networks. But that's me. Okay, I mean, I'm certainly willing to entertain whatever proposal people may put on the table. It doesn't mean that I'm not going to write papers on graphs that are allegedly models of social networks. Why? Because the mathematical problem is interesting. But in all fairness, if you push me against the wall, okay, you will. All right. All right. Any questions from the new generation? My pleasure.